Okay, let's dive straight into an explainer that completely bypasses that usual industry hype of old versus new. Today, we're equipping you with an objective, mathematical framework for actually choosing your API architecture. We're stripping away the buzzwords and we're looking at the hard truths of what makes an API contract literally survive in production, pulling directly from advanced engineering case studies. To really wrap our heads around this, we need to start right in the trenches. Picture this, all right? It's Tuesday. You're the forward-deployed engineer at Pinion Integrations, a mid-market SaaS company. At 2:14 a.m., you are violently jolted awake by a PagerDuty alert. A single, perfectly well-formed partner query just fanned out into 14,000 resolver calls on your backend. You groggily open Slack and see the damage. 6.2 seconds P95 latency, Postgres replica at 94% CPU. So who's the culprit? Well, it's a top-tier logistics partner running an hourly ETL. Because of the way the API was built, they had casually nested their query 4 levels deep. You know, they didn't actually do anything malicious. They just asked for data in a structurally legal way and, well, it was absolutely melting your database. So you jump in, patch the system with a quick depth limit, and roll back the partner's schema change just to stop the bleeding. But by 4 a.m., as you're staring at the logs, the root cause becomes painfully obvious. 8 months ago, Pinion shipped a GraphQL API simply because the procurement team asked for more flexibility during the sales cycle. Turns out, the architecture completely mismatched the actual engineering workload. And that brings us to the real core of our explainer today. How do we actually know which API contract our systems and our customers can survive on by, say, day 90 of production? Because look, flexibility sounds absolutely fantastic in a pitch meeting. But when you are the one managing the infrastructure, unused flexibility quickly turns into a massive liability. Moving into the 4-axis decision lens, focusing on the locus of control. Instead of chasing what's trending on Hacker News, we're going to evaluate these architectures entirely on this locus of control. Basically, where does the burden of decision-making and cost actually sit? Is it on the server or the client? First up is the shape-decision-locus. With REST, the server explicitly dictates the endpoints you can choose from. The contract is basically, we shipped these specific endpoints, you pick one. GraphQL, on the flip side, puts that shape decision entirely on the client. It hands over a single graph and says, hey, ask for exactly what you need. Now here is where it gets really interesting, the cost-locus. This is truly the load-bearing concept of this entire debate. REST implicitly puts the cost ceiling right in the URL space. An endpoint fetching a single user literally cannot suddenly load 50,000 rows of nested data. But GraphQL, it drops the cost into the resolver layer. By default, it's completely unbounded. A 4-level nested query is perfectly legal unless you explicitly build enforcement tools to stop it. Looking at the evolution-locus, we see another massive difference in control. REST forces your partners to migrate on your schedule by versioning URLs, like moving from v1 to v2. GraphQL lets partners migrate on their own schedule by centralizing schema drift into a single graph. But remember, that means you, as the platform, are forced to carry the technical debt of that deprecated field tail. Finally, we have the observability-locus. REST logs are beautifully simple, right? Route, status, and latency. They're easily parsed with a standard ELK stack. GraphQL, however, hides everything behind a single post route. You can't even tell what fields a partner queried without parsing the entire operation body, unless, of course, you invest heavily in setting up persisted query IDs. And hey, just for completeness, we definitely have to mention gRPC, that third axis popularized by giants like Google and Netflix. It uses HTTP/2 and protocol buffers. Much like REST, the shape is server chosen and the cost is implicitly bounded. It's incredibly efficient for sure, but that complex binary format makes it way better suited for internal data center, service-to-service traffic, rather than public, partner-facing APIs. Let's transition to resolving that 2:14 a.m. mystery through some case studies. We're going to apply this new 4-axis tool directly to the Pinion situation to figure out what they actually should have done. The very first step is to mathematically profile those access logs. When Pinion actually digs into the data, they discover that out of their 47 active partners, 31 are just pulling the exact same 12-field customer profile every single hour. They're running totally predictable server-side ETLs. That highly touted flexibility, yeah, it was never even used by the vast majority of their users.
So we scored this workload against our lens. Because read shape predictability is so incredibly high here, and because SDK overhead matters deeply to these Python-based data partners, REST mathematically crushes GraphQL with a score of 18 to 11. It gives those partners exactly what they need in a simple curl request, complete with built-in cost ceilings that prevent 2 a.m. database meltdowns.
But just to prove this framework is truly objective, let's run a rapid-fire second scenario. Imagine Pinion was instead integrating with a mobile-first marketplace partner. We are talking 22 million monthly active users, a super strict 400 millisecond latency budget, and they're operating over 4G cellular networks, where every single screen needs a slightly different data shape. This brilliantly illustrates how the scores flip entirely, because every single kilobyte of overfetching on a mobile network is severely punished by latency, and because the mobile team is already using sophisticated client-side tools, GraphQL completely dominates the scenario, 19 to 9. The 4-axis lens generalizes perfectly, even when the final answer completely changes.
Moving on to 3 common API pitfalls. The crucial point here is knowing your workload deeply. But even with the absolute best framework, you still need to be armed against the most common API design traps you'll face out in the wild.
We really have to bust some pervasive industry myths here. First, procurement asking for flexibility does not mean engineering actually wants flexibility. Second, just because REST is simpler to write in a Jupyter notebook doesn't mean it's simpler to scale for a complex mobile app. And third, shipping any API without a per-query cost budget, that just guarantees a disaster. Let's dig into these specific technical pitfalls, starting with the notorious N+1 query problem. Coined by Bill Carwin, this is a massive issue in GraphQL. It's basically an anti-pattern where asking for a list of users and then their individual posts cascades multiplicatively into thousands of database calls. Unless you specifically engineer a DataLoader, a tool to batch and cache these requests, your backend will absolutely grind to a halt. The second major pitfall is unbounded depth. REST fundamentally avoids this because there is literally no URI path that allows a user to just nest a request 4 levels deep on a whim. But a naive GraphQL server, it will obediently attempt to materialize every single nested field the client asks for, chewing through massive amounts of compute time right up until the server crashes. I'll leave you with this thought to carry into your next API architecture conversation. Which property of your design will surprise you the most when real traffic hits? It is almost always the lack of implicit cost ceilings. Teams love to design for functionality, but they totally forget that architectural choices are ultimately about bounding failure. Does your API design actively protect your database, or does it just leave the front door wide open? The answer to that is entirely in your control.